Hello everyone, I'm Hussein Haydari, and throughout the course of the next few weeks I'll be your instructor and we will be talking about polymers. Polymers are an extremely important class of materials. A lot of my research is actually focused on a specific type of polymers, as we will talk about. But here you can see that it's not just limited to a single class of applications. It spans all the way from the automotive industry. You can see it being used from very old days in cars as the material used in tires, the interior, a lot of more important places as well in a car use advanced polymers. They're used in construction and in architecture. They've become a lot more appealing in the recent years, owing to the new advances in these highly transparent polymers. We will talk about the use of polymers in architecture and construction as well. And the image that you see, the third image, the one on the bottom, is actually a human lung's smallest unit, which is a single alveoli sac. And what it does is it oxygenates blood. This is a lot of what I work on, and it's the use of polymers in basically manufacturing mimics of human organs that would be functional mimics and actually hopefully someday used in an artificial organ. So during this chapter and the next, we will discuss a lot of the topics associated with polymers, but mainly it will be focused on the questions here. We're going to talk about the definition of a polymer. Why is it distinct from other sorts of chemical species and materials? We're going to talk about the typical uses of polymers. We're going to talk about the structural features of polymers, their properties. We're going to talk about how these properties are modulated by their chemical structure, by their molecular weight and their crystallization. We're going to talk about how we define a lot of these metrics, such as crystallinity, and how we can actually induce a high level of crystallinity if it's important to us. And why would it be important to us at all? So this is, I would say, a very important module, as it equips you with all the information that you need, at least at a very preliminary and introductory level, to select a particular material for your application. And so having a little bit of knowledge here would go a very long way in terms of your success in whichever career you choose to pursue. So we're going to look at some very exciting pieces of application and use for this class of material in the next couple of slides. But first, just to get deep into the core without spending too much time on the introduction, a polymer is basically a long chain molecule. A chain of a repeat unit, which we call a monomer. A monomer is a single unit. A polymer is basically, the word is made of these two parts, poly and mer. Poly means many, numerous, and mer means that repeat unit. So if you put a lot of these monomers together, they will construct a long chain, which we call a polymer chain. So here you can see some of the most commonly used polymers. What's interesting is a slight change in the structure of this backbone can significantly affect the properties of the material. So polyethylene, for instance, and polypropylene are both used to make containers, but polypropylene is extremely chemically resistant. So they can use it for containment of acids and bases, whereas polyethylene, although typically used for food storage, isn't that resistant or resistant at all to chemicals. So the only change there is that you've introduced a CH3 group there, and we will talk about what that group is, and it entirely changed the behavior of this material. So this is the really exciting part of it, is that you can actually understand how a tiny tweak can completely change the behavior of the polymer, and that introduces some numerous new applications. The one you see in the middle is PVC, a material commonly used in these large tubes that you use in construction to carry fluids, and also to host cables and stuff. So polyvinyl chloride is also a very important polymer. The difference is that you've replaced that H, the hydrogen, rather than with CH3 with a chlorine. So it's actually these very tiny tweaks that we will see during the course of this lecture and the next few lectures that completely change the polymer. So you can get a broad range of applications with. These are some of the stars and rock stars of this industry, if you will, that have completely changed. And so the companies that have come up with these materials and formulations, or if it was a research lab, has become very successful and known for that particular. So Nomex and Kevlar, for instance, are now widely used for firefighter suits. They've also been used for space suits as well as other applications, but they are known for extremely good fire resistance. If your flame is actually removed, rather than it propagating the fire, it would immediately stop it from propagation. Of course, if you have continuous fire, these are just fire resistant. So they're also impact resistant in terms of a bulletproof vest. So Kevlar especially has a very large impact resistance in that sense. So these two are very important class of these polymers. Another example is ETFE, ethylene chloroethylene. What this material is this very transparent plastic polymer that has been found to maintain its transparency over long periods of time and under a sun. So it doesn't have the brittle, fragile aspects of glass, but it does have the same transparency, more or less. So this was actually interesting. The first time this was used was a rather long while ago, but in the Olympics, in 2008, the Summer Olympics in China, you can see here that this building is the swimming venue. It was called, I think, the not sure, it's the National, I believe it's the National Aquatic Center, but it is entirely surrounded with these sort of cushion-like plastic enclosures made out of ETFE, and it was a beauty. And then ever since then, it caught a lot of attention because it sort of filters out some of the wavelengths of light, but at the same time allows a lot of light to pass through. The transparency is really high, and it actually has a very long life and is rather mechanically robust. It's tricky to build these structures, of course. The dimensioning and geometrical accuracy is really important, especially with materials such as polymers, but they've been used widely ever since in construction. Another application is these superabsorbent polymers that are used in diapers. So a layer within these diapers is actually made of these SAPs, stands for super polymers. What it does is that it encapsulates water to a very high degree. We will talk about hydrogels in a minute, but a lot of these polymers can hold a lot of water content. What that means is that they're extremely useful for absorbing moisture. And so this is something that also has been around for quite a long while. And so you can see there's a breadth of application. Another application is in dentistry for these dentures. So you have here PMMA, polymethyl methacrylate, which is a light cured resin. You use UV light or other wavelength, depending on what initiator you have, and we'll talk about that also in the next few lectures. To actually convert this from a monomer to polymer, and you've probably been either in contact with this material in a dentist's office in the past, or in the future you encounter this material, but it is a very widely used material for fillings as well. So a lot of these light-based polymers that form from liquid resins have become materials useful for 3D printing as well. And that's my research focus, which I'll probably talk about that in lecture 3 of this lecture series, and that would be towards maybe next week. But it has enabled us to do additive manufacturing in a way that's a lot faster, a lot better resolution, as well as the material conversion and properties than what we had with conventional 3D printing. So what we have here is basically a breadth of applications with polymers that actually haven't been around. So what we see here is a breadth of applications that has been enabled by this vast variety of properties that you can get from polymers. And these are all functionally distinct materials. So as we will see, a lot of these polymers have a rather ductile behavior. A lot of them have a more of a brittle behavior, but in general, they have a trend of high deformations, high deformability, as well as rather low stiffnesses. But this can vary a lot by changing the structure of these materials. So what are polymers made of? So polymers are typically made of these two atoms, carbon and hydrogen. So they are, in other words, hydrocarbons. And you do see other elements showing up in the structure. These two are, in essence, the main constituents of this material. So what you see is that carbons bond together to form the backbone, and hydrogen atoms are in the surrounding of these carbon atoms. So there are different classes of these polymers, different classes of these hydrocarbons, in other words, depending on whether they're saturated or not. And what that means is that how many atoms are the carbons bonded to, or in other words, the carbon-carbon bond, whether that's a single or a double bond. So we will talk about that in the next slide. But before we get there, we've got saturated hydrocarbons, which basically what happens is that your carbon is bonded to the maximum number of atoms that it can be bonded to, which is 4 atoms. In this case, you see it's 1 carbon and 3 hydrogen. All of these are examples of saturated hydrocarbons, and what you can see is that all the bonds are single bonds, meaning that you've saturated this carbon atom here. It's been maxed out in terms of the number of atoms that it can connect to and covalently bond to. So what you see here is the smallest hydrocarbon of the family, methane, CH4. And if you increase the number of carbons to 2, you have ethane, C2H6. And it follows this formula here, which is however many carbons you have twice that number of carbons plus 2 of hydrogens. So you have that same formula following through these different molecules, but they all follow the same sort of unsaturated versus saturated scheme. They're all saturated in this. The other variety of that is the unsaturated molecule. The ones that have a double bond here, in which case you haven't used the full potential of carbon to bond to the other atoms. You only have 3 atoms connected here, and that is 1 carbon and 2 hydrogens. So it's actually, however many carbons you have twice as many hydrogens. And then another example is if you had a triple bond, and in this case you have only 2 atoms connected to carbon, and so you've got, again, an unsaturated carbon. So when we're talking about saturated, we mean that you've saturated the number of bonds, chemical bonds, valent bonds that you can have on the carbon. And so in both of these cases, it's an unsaturated molecule. In this case, ethylene or ethene, and acetylene or, again, ethine. So basically, that's another sort of organization or classification of these molecules. Now, again, back to the structure of polymer. A polymer is a chain composed of many of these monomer single units. And in this case, your repeat unit is a C2H6, for instance. In this case, C2H4, because you don't have the hydrogen, it's replaced with the next monomer. So in other words, you've got that same molecule that we had here, for instance, ethane, or the double bond version of it, ethylene, and you've broken that double bond in order for it to connect to another carbon. Okay, so you break that single, basically the single bond of this double bond here, in order to saturate it into a reaction where it connects to the units right next to it. So basically, it's just a very long hydrocarbon. In other words, the molecule that you see here or here is a monomer. If you put a lot of these together, it's still going to be a hydrocarbon molecule. It's just a polymer, which is a long version of this monomer. So a lot of these polymers have a more complex structure. In this case, you've replaced one of these side groups with basically what we call a ring. It's an aromatic ring here, and we will learn about the properties uses in this material. And in a lot of the cases, you have a lot more complex sort of monomers or units. In this case, nylon, which also has a very application space. But in all these cases, you have a monomer unit that is repeated throughout this long chain back. So how do we produce? We know what they're made of, but how do we actually produce them from monomers? There are lots of ways. One of the most dominant ways is free radical polymerization. And what this means is that you have a radical species, and so this is the reaction cascade. So the cascade is a chain of reactions. So in this case, the first reaction in this cascade is a free radical that reacts with your monomer in this, and then it breaks that double bond into, and the reactive free radical is actually now stuck to the C there, and the other C has an electron there. So it's ready to have a reaction. In other words, we've initiated the cascade. Now, if it meets another monomer, another ethylene molecule, what would happen is that it would actually propagate. And so now these two will connect, and still the C all the way to the right has an extra electron. So now this entire thing is ready to have another reaction with another ethylene monomer. So this chain reaction causes a chain molecule, which we call a polymer. So it's all about that bond there and how it breaks, how we can induce that initial phase and then have the entire cascade happen. So another example, so we will look at different initiators, but what an initiator is that molecule that when you break it, it produces your free radical. So that free radical can then start a cascade of reactions. So in this case, you've got this molecule as your initiator. And this initiator, when you break it or you cleave it into two pieces, it can actually start a reaction. And it's basically, now it's a radical species. And so you've got two of these halves, each of which is capable of initiating a cascade of reactions, which basically leads to a polymer. Okay, so we're going to talk about molecular weight of polymers. Now, as you know, in this sort of reaction cascade, you can get numerous different lengths of polymer. So we don't know for sure whether this chain reaction here will terminate after 10 or 20 or 100. What it depends on is how much time you give it, the temperature of the environment, the availability of these initiators, but you can never ever control exactly how many monomers are in your chain. So no manufacturing company, no chemical producer can actually guarantee that we've got all 25 monomer length polymers. They have to then filter it to get to that particular number of monomers. Throughout the production phase, there is no way to precisely control how many of these units you get, because you've got all sorts of reactions going on at different phases, and you've got lots of these different propagating dimers or other polymers trying to get larger and larger, competing against each other. And so at the end, you're going to have a mix of all sorts of polymer lengths. So what happens is throughout the polymerization, you get different lengths, and that means you get different molecular weights. So first of all, what is a molecular weight? What is molecular weight? What it is the weight per mole of this species. Now, what is a mole? It's a certain number, 6.022, 10 to the 23 of a particular thing. So if that thing is this particular polymer, that would be 1 mole of your polymer. If that thing is water, it would be 1 mole of H2O. So depending on what you're talking about, we can have 1 mole of pencils. That is that certain number of pencils. So in this case, we want to know how much a mole of these molecules, here these polymers, weighs. And so the problem that we have is that we don't know exactly what the precise number of monomers is, and it isn't something that's uniform among all of these. So what we have to do is to take an average. So we have to take an average of the molecular weights of all of these species here. Some of them may have, let's say, 50, some 55, some 45. So what we do is once we've synthesized the sample, we take it and we do a measurement, and that's what we use for the molecular weight. So we always end up with a distribution. And this distribution, for example, shows us that we have a maximum of a certain molecular weight. Maybe in this case, it's like 25. And then we have a small population of the molecular weight 10. So you have a distribution. Some have succeeded in probing quite a lot and building these longer molecules, and some haven't and have stayed at lower polymer chain lengths. So you get these distributions out of your production results, and this is done via characterization. And then what you do is you then use this distribution to find out what your average molecule is. Now, this is an important thing to note, and that is you can draw this distribution based on number fraction, which is how many you have in every basically interval, or based on weight fraction. So here, for instance, you're saying that of the length 10 to 15 monomers, so that is how many monomers you have in your polymer chain, of the length 10 to 15, I've counted and I've only got, you know, about 15% of all my polymers in this mixture have gone all the way to 10 to 15 units. And so what this tells you is how many, or the number fraction out of the overall number of molecules have this particular length. Now here, or this particular molecular weight. So here what you have is that it's a weight fraction. Or in other words, what it's telling you is that how much of the weight of this entire mixture is basically 10 to 15 times 10 to the 3 grams per mole, or, you know, X number of units. And so you can draw this for every production sample. You can draw this either based on the number fraction or the weight fraction. And we will do a lot of examples both here and in the basically the synchronous part to get familiar with this concept. But the important thing to note is that when you do this reaction, you'll end up with different molecular weights or lengths of this chain, and so you'll always have a distribution. Now, again, how do we define molecular weight? It's the mass of a mole of chains, or the mass of a mole of pencils, or a mole of whatever that you are trying to find its molecular weight. Now, so here again, it's showing the distribution, and it's typical that the weight average is larger than the number average. I will leave it to you to think about why that is, but for polymers, it's typical that this happens. I'll give you the answer when we're in the class, but basically have a thought about why the weight average is typically higher than the number average. Now, how do we calculate that? It depends. You're either doing a number average molecular weight or a weight average molecular weight, but in either case, you have to find the fractions. In this case, it's the number fraction, in this weight fraction. And for every column of that distribution, you multiply it by the molecular weight, and then you sum all of those together. So for instance, here, you have the molecular weight here. Let's say it's 10 to 15, so you pick the average 12.5, and you multiply it by the fraction here, which is 0.15, for instance, and you sum that up with the next one, which is the average of this interval. So it's 17.5 times 0.23 maybe, and then you sum that up with the next one, which is 22.5 right in the middle, times the fraction of this, which is like maybe 27, and then you sum it with the next one, so on and so forth. So it's the sigma of all of those. And once you actually find that, so you actually now you've got the total weight of the this is another way to calculate this. So this is one way, and the other way is if you've got the sample and you weigh the entire sample and divide it by however many molecules you have. It depends on how the data looks. If the data gives you the total weight mixture and it also tells you how many molecules there are, then you can actually use this formula. If the data gives you the fractions, either number fraction or weight fraction, and also the the molecular weight, then you can actually use this formula. So what I will do is I will basically leave it at here, and this example will be the conclusion of this part of the lecture for this week, and we'll continue next week. So this example is the last example, and this will be the last slide, and we will continue in the next lecture about molecular shape and structure of the polymers. So before I conclude, let's do this example together. So if you want to do it on your own, it's fine. The idea is that it doesn't have to be a polymer that we're calculating the average mass of it. It could be the number average weight, or the weight average weight of a class of students. So for instance, you guys, if we figured out what the fraction of you having a weight of about 100, 120 pounds is, and then for 140 and 180, etc., we could find what the average weight of the students of this class is. So here in this example, you have one student with 100 pounds, you have one student with 120 pounds, and so on and so forth. You have 3 students with 180. So what you do is now you've got the number fraction here. So basically, how do we calculate the number fraction? That's the first step here. The way you do that is you have the summation of the students. There's overall 10 students, and then you divide the number of students in each category by the total. So you've got 0.1, for instance, at 100. You've got 2 divided by 10, 0.2, have a weight of 140. And so if you were to calculate this, here you have 0.2 is 2 divided by 10, the total count is what your number fraction is for weighing about 220 pounds. So what you do is you actually calculate by multiplying this number fraction here by that weight there, and then you sum up all of what you have there in terms of your xi times basically mi's in order to find your overall. And then what you do is you report that as your number average. Or you could do the same if you have a weight average. So in that case, what you would do is you would look at basically what percentage of the weight of the class is actually students with a weight of 100 pounds. So what would you do? In that case, you have to find the total weight, divide the weight of that particular group by that, and that will give you the weight average, 0.054. And so now that you've got that, you multiply it by the mass of that particular category, and you sum it up with the rest. So in this way, what you can actually do is that you can, first of all, calculate your number fractions and weight fractions, multiply them by your mass, sum it up, and then once you've summed that up, you can find out what your number average mass or your weight average mass is. So we will do a couple more examples in class, and that way we can all get a good understanding of how it works. Thank you, and we will continue this lecture in the next session.